The webinar, we should be all good to go.
So we'll go ahead. Sure. All right. Thank you so much, everyone, for coming tonight. I just wanted to, thank you for coming to Popping Science Bubble. I'm going to start with our land acknowledgement statement, and then I'll introduce the Science Bubble program. So Berkeley Public Library buildings are built on the territory of the Kuchian within the homeland of Chochenyo-speaking Ohlone people. We acknowledge and honor the Ohlone people who have lived in Berkeley and throughout the East Bay since time immemorial. The library recognizes the Berkeley residents have and continue to benefit from the use of occupation of unseceded stolen land, and we pledge to recognize the permanence and the rich contributions that the Ohlone people continue to bring to the city of Berkeley and throughout the East Bay. We celebrate the strength of the Ohlone people and their culture. The Berkeley Public Library is committed to helping create a more just and anti-racist society and to furthering the visibility and celebration of Ohlone authors who are specific to the East Bay and Ohlone culture in our collections and programming. This is a living document that was co-written by Ohlone cultural leaders Vincent Medina and Luis Trevino at the Berkeley Public Library. And Vincent and Luis are hosting a monthly Cafe Ohlone program with us. So if you'd like to come to their cafe, try some native food and learn about native culture, that happens usually the third Wednesday of the month. So check out our calendar and you can register to join for that. So welcome to Popping the Science Bubble. This is a monthly seminar series that aims to share new research findings from grad students and postdocs at UC Berkeley with the general public and create constructive discussion about a variety of science topics. We have two speakers at each seminar who will talk about their current research or a topic that they find really interesting. The organizers are two graduate students at UC Berkeley, Kaylin Swong and Daniel Bretthauer. This program happens every third Tuesday of the month at 5:30 p.m. at the library and on Zoom. So if you're interested in checking out their past seminars, you can visit their website, visit their YouTube page, which has a lot of just like really great programs. And you can sign up for the listserv to keep in the loop for upcoming seminars. All right, thank you so much. I'll let our presenters take it away.
Thank you, Kelsey. And thanks for everyone for showing up. My name is Kaylin, and I am one of the co-organizers of the seminar. And like Kelsey said, we have a host of videos from past seminars that are on our YouTube page. And if you're interested in getting more information, including resources and Q&A from the speakers, we'll send that out after the seminar. So please join our mailing list if you're interested. We only send 2 emails every month. So it's my pleasure to introduce our first speaker today, Isaac Joyner. Isaac grew up in Indiana and studied chemistry and French at Indiana University. After completing his undergraduate studies in 2020, he moved to Berkeley to pursue a PhD in chemistry at UC Berkeley. Outside of research, Isaac is a climber, crafter, and most recently a weaver. So please take it away.
Hi everyone. I guess I don't know if this is everyone can see me. So thank you all for coming, and I'm excited to tell you a little bit about the object of my research at UC Berkeley and the stuff that I'm really interested in, which is enzymes. So I started my chemistry career at IU and really focus on full-on synthetic chemistry, organic chemistry. So in the world that is chemistry, there's sort of what you would think of when you're thinking of a mad scientist, of like flasks with spinning things in it and magnetic stir plates and stuff. That's sort of the world of organic chemistry, and sort of fell in love with how we can make molecules, what molecules can do for us as people and in society. But one thing that was that I had to reconcile with was that a lot of the things that come with that we use to make molecules are derived from sort of petroleum-based products, and a lot of the reactions that we run are in these solvents that are highly toxic or at higher temperature. We run reactions at high temperature or under very harsh reaction conditions. And so, over the course of my undergraduate studies, I became more and more interested in this idea of using enzymes to do chemistry that's interesting for people and for society. And so here at Berkeley, I've worked in the Hartwood group. It's a picture of our group. It's a pretty large group, and we do a large variety of things, but our subgroup focuses on using enzymes to do interesting chemistry, mostly through the use of metals other than the ones that you would find inside of proteins. And so I won't super talk about the exact research that I've done over the course of my PhD, and mostly focus on just what are enzymes as a concept and how are we using them in the lab. And so to start, like, why would we care about, it says, why do we care about enzymes? And I think to take an illustrative example of why these are so interesting and powerful, you can just look at basically everything around you in nature, right? And so as an example, the poison dart frog, this very brightly colored frog, and eucalyptus, right? This very strong smelling plant. And what causes these things are molecules, right? So some of the dyes, the pigments inside of poison dart frogs are these carotenoids, which are these highly conjugated molecules, and they are very brightly colored. And then, some of the products, the natural products inside eucalyptus that make it smell are things like the one that I've shown here, right? And so you can already tell they're very complex molecules. That's basically what I wanted to get you to see from this, is that they're very complex, but nature makes them from these very, very simple things, CO2 and water, and over a course of many iterations through many different organisms, you get these very complex things. And the way that it creates these products is through mostly through the use of enzymes. And as an added bonus, these reactions are protected at room temperature for the most part, and water. And so we don't need things. Nature doesn't need things like organic solvents that are highly toxic to people and to nature, and it doesn't need things like increased reaction temperatures. And so, what is an enzyme? Well, enzymes, to understand an enzyme, you sort of have to understand what a protein is. And so this is proteins, the basics. And so proteins are made up of amino acids. There are 20 of them that are essential to life. I've just shown 3 here. They're these small molecules, and when they're joined together in a specific sequence, they form something called a primary structure. And the order of these amino acids is encoded in DNA. And then, after we have this long chain of amino acids, it folds up into this initial structure called the secondary structure, which adopts, generally speaking, either sort of an alpha helix-like structure I've shown on your left, or this sort of beta sheet structure, which I've shown on your right. And then, putting all these secondary structures together, they can fold into these even more complex sort of structures, the tertiary structure, which really gives a protein a 3-dimensional shape. And then in some cases, these tertiary structures can aggregate and create macromolecular structures, which are for the quaternary structures. And so we formed this really, specific and unique 3-dimensional shape. And it's really this structure that informs the function of the protein. And so now we know a little bit about proteins, but what about enzymes? Like, what is the difference between a protein and an enzyme? And so I think a good analogy for the difference between a protein and an enzyme is thinking about them both being tools, but them having vastly different functions. And so proteins, an enzyme is a protein, but a protein is not necessarily an enzyme. So proteins can serve roles like structural roles, like this sort of steel framing of a building, but not necessarily sort of functional roles like you would for a hammer. And the other thing to sort of understand is the idea of, so I guess it's a tool that provides a structure, or tools that sort of facilitate the task. And so the other thing to sort of understand is that enzymes are catalysts. So this is just sort of the definition of a catalyst, but it's a substance that increases the rate of a chemical reaction without necessarily being consumed in the reaction. And so this is sort of a graphic of what this looks like, and as just an analogy of why you might use a catalyst. If you were going up a hill, I guess if you're taking a load of rocks from point A to point B, it might be downhill, but in order to get to point B from point A, you might have to go up a hill. And so it's sort of a catalyst doubles off the hill and allows you to get there more quickly. And so I think that a good analogy, to take this hammer analogy even further is if you were trying to get a board with a nail in it, a nail plus a board might be point A and a nail and a board might be point B. But obviously using a hammer to nail the nail into the board makes the process go much more quickly. And so then just some sort of real world examples of, enzymes at work. The enzyme that's included in a product like lactate is lactase, which catalyzes the hydrolysis of lactose, which is two sugar molecules attached by this oxygen atom. And so it happens much more quickly in the presence of the enzyme, and it doesn't break apart very quickly without it. And then, if any of you guys are lactose intolerant, I'm sure you can appreciate that when you take lactase, lactate, you feel better, which is because the lactose is coming apart more quickly. And then, just one more sort of illustrative example of why enzymes are powerful and the sort of things they can do. Carbonic anhydrase is an enzyme that adds a water molecule to carbon dioxide and allows us to regulate the pH of our blood, and also allows us to transport a gas through our body. And it increases the rate of this reaction 10 million times. And so it's this really essential reaction, and it really is a powerful thing for us as people. And so how do enzymes work? Well, enzymes, like I said, are these three-dimensional structures, and they have this little hole in them, or a little place where the chemistry happens, and that's called the active site. And so a substrate that fits inside of the active site, and that really specific three-dimensional structure will go into the active site, and then some chemical reaction will happen and will liberate a product. And so that's great, and it's awesome that they can keep doing that and keep doing that and keep doing that. But enzymes aren't necessarily stuck in their ways, and this is sort of the toehold that chemists have and us as humans have for starting to use enzymes for our purposes. And so, if there's some sort of selective pressure, whether it's natural or artificial, say we wanted to perform a reaction on, instead of the circle substrate, a triangle substrate. Well, an initial protein, that pocket might be a bad fit, but through rounds of evolution and introducing mutations to the protein, the pocket and the three-dimensional shape can be gradually reformed for a new substrate. And so, over time, we sort of get these, reshaped proteins, and we can perform reactions on new sorts of substrates. And so, just to draw a parallel, you can think about artificial selection, where you might take something like a pug and turn it into something else, or a wolf and turn it into a dog over the course of time. And then draw the parallel to something like natural selection, where we have some selection pressure to do something, and then evolution sort of happens. And so we're making changes to the proteins and getting some desired outcome. And so how do we use proteins synthetically? The graphic on your left is sort of showing, all of chemical space, where each box might represent a specific reaction with a specific substrate. And so the yellow box could represent the reaction that is catalyzed by a protein. It's its native reaction, its native substrate. It's really well formed for that specific reaction. And then this idea sort of artificial selection, we have this, it's also true that sort of most proteins can accept a substrate that maybe looks sort of like the substrate that it naturally works on, but maybe not exactly. So instead of working on something like a circular substrate, it might work on something like an oval substrate and catalyze the reaction on that. So around this sort of area of natural reactivity, we have this sort of promiscuity space. And then lastly, there's this idea of expanding the chemical reactivity of proteins through introducing mutations to the protein, redesigning the sort of shape of it, and accessing new types of reactivity. And so, what are the frontiers of this field? Artemisinin, nowadays we're making these very complex molecules like artemisinin, which is an antimalarial, and was really sort of infeasible to synthesize synthetically, and in most cases needed to be sort of harvested from a natural source, but now we're able to biosynthesize the molecule by using yeast and introducing enzymes to do the chemistry for us. And then, this is remdesivir, which is a drug made by Merck, and it's a COVID antiviral. And it was this really beautiful, sequence of enzymes that catalyze the reactions in sequence. And then, in this new area, I would say the final frontier of proteins maybe is this idea of computational design of proteins, which won the protein folding prediction won the Nobel Prize in Chemistry this year. And nowadays we're really able to use our knowledge of proteins and design new ones that can bind targets or perform reactions. So that's sort of all I have for you today, but I just wanted, it's mostly just a primer on proteins and enzymes and how cool they are. Yeah, I'd be happy to take any questions.
I guess I could start off. So you kind of hinted at the very beginning that your work kind of focuses on when you kind of begin to add metals to this. And so what kind of new and interesting things does that do?
Yeah, so it's estimated that up to 50% of proteins contain a metal for either sort of structural reasons or functional reasons. And one of the sort of the first line of metabolism of things that we eat and maybe drugs that we take in our body happens with these proteins called cytochromes P450, and they contain this they contain sort of this cofactor, but with an iron atom instead of an iridium atom. And they transfer an oxygen atom to the molecule. And then by virtue of adding the oxygen atom, we're much more able to break down the molecules. And so they catalyze the reaction by sort of generating an intermediate where you have something that looks like this, but with an oxygen atom, and then that can transfer. And so our research in our lab, takes expands on the idea of substrate promiscuity. Instead of thinking about, okay, we have a substrate and we might be able to catalyze reactions on substrates that look sort of similar to it, we sort of think about intermediate promiscuity. So instead of forming something that looks like an oxygen atom there, forming something that looks very similar and is electronically very similar, but might transfer something like a carbon atom instead of an oxygen atom. And so, yeah, we like to think about the sort of reactions that can happen by replacing metals or expanding the sort of repertoire of reactions that nature catalyzes. Yeah.
One of the two molecules you showed on your last slide, I think the anti-malaria one, you said that it's very difficult to synthesize or create a synthetically. Can you talk about what makes it so difficult, or like in general for enzymes?
Yeah. So we draw this thing in this two-dimensional way, right? But each one of these sort of wedges and dashes indicates a three-dimensional structure. And so molecules aren't these flat things. They're these sort of like, very three-dimensional objects. And it turns out that making those sort of three-dimensional objects is very challenging and requires development of chemistry that can take years to develop, and it might not work super well. And then the other challenge with it is that something like artemisinin and antimalarial needs to be produced on a huge scale, and it needs to be deployed in countries where we just don't have the money to be spending on making sort of very expensive molecules. And so there's a cost aspect to it too. But enzymes, like I said, are these like three-dimensional objects, and so we're able to sort of very finely control the three-dimensional aspects of the synthesis of the molecule. And then the other thing is something like artemisinin is a natural product. And so in biosynthesis, you can sort of identify the sequence of enzymes that would make the molecule and normally inside an organism and then put it inside of an organism that is easier to work with. Yeah.
And some of these tests then, can you elaborate slash give your opinion on where do you think these computational design tools slash AI tools are gonna lead the future of this?
Yeah, so I think oh sorry, I was just gonna play the animation again. Something like this, right, which is just, I don't know if I can play it again. We have a sort of a protein that we're trying to develop a protein that will bind to this. So I think that we're gonna be able to do and we can do pretty well. But designing proteins that actually sort of perform functions is still very challenging. And so I think that there's a lot of opportunity to develop maybe new medicines that are protein based. Think something like insulin is a protein, or there are more and more and more you're seeing medications that are not small molecules like this, but are what we call biologics. And so they're proteins that act as medicines, but because they're proteins, they have certain liabilities, like insulin and a lot of proteins were evolved to be inside of a cell and were evolved to be sort of transiently active and transiently present. But that doesn't really work if you have to have a molecule that's super stable on a shelf, and then can be injected into a person and stay and then be transported inside of a cell. And so I think there's a lot of opportunity to design proteins that have functions that we want, but are much more stable and have less of the liability of natural proteins.
No questions on this? Then I think let's give Isaac another round of applause. While we're switching over to our next speaker and sharing his stuff on Zoom, I'm going to go ahead and introduce him. Our next speaker is Felipe Gonzalez Cataldo, and he is a Chilean physicist specialized in planetary interiors through the study of the physics of materials under extreme pressure and temperature conditions. He grew up in a small town in Chile called Saladillo, and then moved to Los Andes to complete elementary and high school. Afterwards, he moved to the capital, Santiago, to pursue a bachelor in physics at the Universidad de Chile. Felipe earned his PhD in physics in 2015 from the University of Chile and is currently a project scientist in the Department of Earth and Planetary Sciences at UC Berkeley, where he's part of Professor Burkhard Militzer's research team. His work focuses on applying molecular dynamic simulations of materials based on first principles to understand thermodynamic and electronic properties of matter at the atomic level. And when he is not doing anything research related, he is either going to heavy metal concerts, which includes attending the 70,000 tons of metal cruise that sails the Atlantic Ocean full of metalheads on a journey of 5 days of nonstop metal concerts on board. Wow. Maybe we'll hear more about that too if we have more questions at the end. But please take it away.
Did you share the screen? Your screen up?
You might not be in the meeting anymore. Of course. You still do need to share. It's not going.
Sorry, technical issues.
Maybe you could tell us a little bit about the heavy metal music that you enjoy while you.
Sure. Working out. And there we go. Okay, sorry for the delay. And thank you everyone for coming. I'm really glad to be here.
You can also do.
Yes, I got it. Yeah, okay, thank you very much for reading now. So thank you very much for coming. I'm really excited to tell you about my work, which is related to what you're seeing right now on the screen, which is related to study the deep planetary interiors using atomic physics of minerals. So these are two worlds that we're connecting from the very, very tiny to the very, very large scale, where we can learn about what's happening inside very different planets, not only in our solar system, but inside other exoplanets using physics of minerals. And I do this in the Department of Earth and Planetary Science here in Berkeley. And I would like to start by showing you how we think more or less that planets form. So what you should have in your mind when you think like planets form is more or less what ChatGPT has in his head when you ask him like how planets form. So when I asked ChatGPT what he thinks like planetary formation looks like, he drew this crazy thing. But it's actually not that wrong, because when you see a planet, you see usually all the planets around it. There's a protoplanetary disk where things are going around the star. And there seems to be like layers inside of this where like there's a lot of temperature and things happening. And here's like more of an idea of ChatGPT of what's happening with the particles and the atoms inside the planet. So somehow it's telling us that things are changing. And the models that we have to form planets are based on this idea that there are many rocks that are around every single star. When they start colliding with each other, they stick to each other. And when they are able to attract other rocks gravitationally, then it starts a runaway accretion process where the more it grows, the larger the gravitational pull. So this thing grows larger and larger, and you end up with this massive body, which is just made of molten rock. We think that this is generally the initial state of almost every single planet. So we wonder then, it's like, well, what happened to those rocks? It's like, what happened with this rock that end up in something as Jupiter versus something like the Earth? Why are they so different? And I will tell you in a minute why we have found like many planets that we do not have in our solar system. So the two main methods that astronomers use to detect exoplanets, these are planets that are going around other stars, not our sun, are the transit method and the radial velocity. So the astronomers don't see this. The things are too far away to actually see them. What they say is that if you look at a star, the brightness of the star decreases a little bit and then goes back to normal. And that is an evidence of an eclipse of this planet going in front of the star. And the astronomers can measure not only the radius of the planet, how big the planet is, but the atmospheric composition as well. So what the atmosphere of that super far away planet is made of. And with this radial velocity method, there's this thing called the Doppler shift, where basically the planet pulls the star back and forth and moves these lines that are signatures of the chemical compounds inside the star. And by the motion of these lines, you can detect, you can measure actually what the mass of the planet is. So with mass and radius, you can have an idea of more or less what this planet can be made of. Because if it's very low density, it must be very puffy, made of a lot of gases. But if it's very dense, it must be kind of rocky, right? So this was the Nobel Prize of 2019 to Didier Queloz and Michael Mayer for the discovery of the first exoplanet in 1995. So imagine that. I see like the audience here, we are all kind of in elementary school, right? By 1995, this field didn't even exist back then. So this field is very young, and the discovery of exoplanets has connected to many other fields that I will show you in a minute. So when we look at the data, we now see that we have more than 5,500 exoplanets already discovered and characterized to different degrees. When I started in this field, like about 12 years ago, there were just like 400. So this thing has grown rapidly, and we know that there are many planets that are not the typical gas giants like Jupiter. They are not like the Earth, but they are these super Earths and sub-Neptune planets that come in between, and they seem to be the most common type of exoplanet, and we do not have any of those in our solar system. And then the immediate question is why? Why don't we get didn't we get these very popular type of exoplanets? And in the data, they look like these two populations where you can see that the Earth is here in this radius, Neptune is over here, like 4 Earth radii, and there are these two populations. There are many planets with these radius and many others with those other radii, and there are not many other planets with radii in between. So that's what they call the Fulton gap or radius gap, and seems to separate planetary species that again we don't have in our solar system. And now the statistics shows that basically 1/3 of the planetary types that exist in our galaxy are these super Earths, these type of Neptune planets and gas giants. Only 4% are terrestrial, which is kind of disappointing, but it is what it is, right? So there are many categories of these planets, and they're very different in circumstances that these planets go through that are interesting to study. For example, these lava worlds are planets that are so close to the star that they get tidally locked, like the moon always faces the same face for to the Earth. But the fact that they is facing the star makes the one side of the planet always molten while the other may remain still rocky. So that is like completely different physics to what we're used to. We don't have anything like that here in our solar system. And we have like these ocean worlds, hot Jupiters, cold gas giants that we really need to explore in more detail in order to understand how they came to be. So in order to study this, we combine like several different fields actually. We use astronomy with geophysics, chemistry of molecules and atoms, and thermodynamics to understand what happens with these different materials. And one of the the exoplanetary systems that has been studied a lot actually is this TRAPPIST-1 system. That is a system of 7 exoplanets that are more or less on the radius and mass of the Earth. And you can see that the orbits, however, fit all in the orbit of Mercury, which means like all these 7 planets are closer, way closer than Mercury is, which is the planet that is closer to our sun in that solar system, and they seem to be living very happily there. Why aren't there gas giants like Jupiter? We don't know, right? We need to study the formation. And in terms of the composition, how do we even know what these things are made of? Well, it turns out that Earth is the planet we obviously know the most about because we're sitting here, and we can actually use earthquakes to do seismic tomography. And this is basically the same as when you go to the hospital and you take a tomography of your body to know what's inside you. Earthquakes can be used to literally do a tomography of the Earth and different layers you have inside our planet. And the seismic waves are related directly to the Earth is made of, because the sound speed at which the earthquakes propagate is unique in each material. So by knowing how these velocities change inside the planet, we can figure out what the different layers are made of. So it's a really nice interplay between material science and seismology that helps us understand planetary science. And we know minerals because we go to do field work. We understand like there are many meteorites that fall in the Earth that tell us about like things that were floating around the solar system. We collect the rocks to know more about the Earth. So we know more or less what the Earth is made of, but we can start studying other planetary systems by looking what other minerals these other planets are made of. And the key tool that I do in my research is use quantum physics, which is simulations with using quantum mechanics of these atoms to verify and predict what the properties will be at the insane conditions that you have at the center of these planets. Sorry about that. We covered it. Sensitive. Okay, there we go. So inside the Earth, there are many things happening, and convection is one of the most important phenomena. Convection is when you have like this motion of material. This in this case is solid material that is rising up due to the difference in temperature, and it's actually what moves the tectonic plates that cause earthquakes, right? So this motion happens in the scale of millions of years, right? But it's basically the same that happens in your miso soup when you go to a restaurant. So I suggest you that next time that you eat a miso soup, you pay attention to these convection cells that they are rising from the bottom of your plate, because it's exactly what's happening inside the Earth. And we can study these phenomena in laboratories to understand things that are happening at global scale in the planet. So one of the experiments that has been done in order to understand what happens with materials at very crazy conditions, like for these super Earths, for example, is this experiment done in Livermore. And this is like an amazing achievement of technology and science, because it's a laboratory in Livermore that is meant to do fusion by inertial confinement, where they have 200 lasers that have been like super amplified. They're terawatts of power that are designed to get to that chamber over there that is like about 10 feet high at the same time and hit a target that is smaller than your eye. This thing, imagine it's like a building. So you can put like 3 people on top of each other here in this chamber. And these lasers that are like terawatts of power come to that very tiny sample, and they compress a capsule that is inside that is like the retina of your eye, and the whole experiment lasts 10 billionths of a second. You have only 10 billionths of a second to detect absolutely every step of the process, how this thing compresses, increases pressure, temperature to reach fusion. And they already did it 2 years ago for the first time. So we have reached ignition. Besides reaching ignition, they can compress also materials that are relevant for planetary science, like iron. And this is really like when Goku like collected a lot of energy and threw it to an enemy, right? And this energy is like very dense and gets to a material. And the idea here is to do fusion, right? Very much like in Dragon Ball, when you get like 2 things and then you get just one as a result. It's the same thing. Here's like hydrogen making helium, right? And when we're interested in minerals, what we basically do is launch a shock wave inside the material that compresses it to really crazy temperatures and pressure, and they are able to monitor where the material melts. And why is that important? Because that tells us about the state of the core of the planet. So when we look at this stage that I told you earlier, when you have this early planet that is completely molten, at some point this thing will start crystallizing, right? It will start freezing because it loses temperature, and you end up like in billions of years with a completely molten planet. We're not there yet because we still have a liquid outer core in our Earth, but it will freeze at some point, right? In just a few billion more years. So we have to study like material properties actually to figure out if this thing will crystallize from the bottom up, like the center outwards, or from the top downwards, because that's not really evident. And that crystallization process, it's all connected to material science. So I don't expect you, of course, to understand this, but basically we can figure out what a planet is made of by solving like these type of models where we combine the data that we have from experiments, the data that we have from our simulations, and we plug it here to this machine to figure out like what are the likely components of a type of a planet. And since we already know from astronomers what is the radius and mass of the planet, we can constrain the composition. It's pretty cool because we do it all the way from here, and these planets are like super far away. Okay, we can already tell what they are made of. And so far, our simulations, at least of iron, this is something I've been working on, show that it's very unlikely that super Earths will have liquid outer cores. And that is extremely relevant. This happens because the melting temperature of iron increases so much with pressure at the condition of these very large planets that it's very hard to maintain liquid iron just because the melting temperature is high. And that is important because if you don't have a liquid outer core, then you may not generate magnetic field. Magnetic field on Earth, like why our compasses work, is because we have a magnetic field that is originated from the very center of the Earth, doing this convection at the center, at the core. So if these planets don't have liquid outer cores, probably they don't have magnetic fields to protect themselves from the radiation from the star, and probably it's less likely that these planets have life because they're exposed to the radiation directly. Other crazy experiments that have been done here in Livermore, people we collaborate very often with, is when they made diamond out of plastic, literally. And with those lasers that I showed you at the beginning, what they did was to take polystyrene, which is like a plastic that you made this type of cups from, and they compressed it to such high pressures and temperatures that they broke every single bond between the hydrogens and carbon atoms, and the carbon was left to such high pressures that they formed diamond, and they literally saw in the experiment nanodiamonds forming from the plastic. So this is like important not only from a chemistry point of view, but because it also tells us that there might be diamond raining in Neptune, because the conditions are exactly the same, and the chemical composition of Neptune is very similar to those of plastic. It's like carbon, hydrogen, some nitrogen, and they dissociate and form these solid diamonds. So for Jupiter, we've learned also with our simulations that rather than having a compact core here surrounded by these gases, the situation is kind of different now, because we discovered that the core gets diluted. There are new chemical reactions that occur like inside Jupiter, and we now think that the core is entirely diluted and goes like almost to half the way of the planet. And these predictions have been confirmed by the Galileo probe, which is going around Jupiter measuring the gravitational field, and they literally put this what was like last year, 2022, 3 years ago, that the measurements imply a dilute core in complete alignment with what we predicted from our chemistry calculations from quantum mechanics of just atoms. So it's pretty cool, and we've been doing like many type of progress in this field, combining interesting questions with interesting simulations that we can do to figure out what's happening inside very different worlds. So I will leave you with that, and I'm happy to take any questions. Clear.
Yeah. Once you do a prediction of how a planet is made of, is there a way to verify it? Of course,
Yeah,
like
that's
I think for like planets that are like really far away, probably not, but the
Right.
ones that we
right.
are close.
This is, if you imagine, like, just stay with Earth. How do we even know that there's an iron core inside Earth? You don't even have to go far, and nobody can like answer that question directly. There's all this like indirect evidence that tells you that that must be the case, and that must be consistent with all sources of like independent evidence. So of course here we have way many more parameters to play around with. There's less constraint, but then this field is all about proving your colleague wrong, right? So someone does a calculation, it's like, I don't think that was wrong. I will assume something different, and we'll get something else here wrong. And then like they fight against each other until they reach an agreement. It's like, okay, we realize that like among these ranges, like these must be like the type of composition. It's never like a unique composition, but you can constrain it pretty much to a very decent level that you can make progress. That's the goal. Yes.
I was just curious about what differences in like, climate systems or surface topology you might find on a super Earth with like a solid core like that.
Well, you ask like when you have like this frozen cores in particular, or like in general, like Jupiter gaseous planets.
I think more in the example of like a frozen core. Like you were.
Okay, well, in the study that I like consider, I didn't consider any substantial atmosphere. So like any climate model was disregarded in, because to first approximation, I want to understand the basics. I wouldn't know. I don't think like it would play much a role in the atmosphere. It's more or less like this protecting magnetic field interacting with the particles that come from the star. Yeah, I don't think they will affect the climate very much, but there are many cases of these tidally locked hot Jupiters where the thing gets way more interesting because it's like so hot and just gases on one side and so cold on the other that you get like winds that are crazy that are going like around the planet, and it's definitely something a case to study more deeply. Yes, crazy weather.
You mentioned this both super Earth and the Neptune line
Mhm.
are the most common ones that you found. And the super Earth may have the frozen cores. What do we know about the Neptune ones?
So the thing is that for Neptune, sub-Neptunes, it's not that easy because then I do have to take into account the atmosphere because these radius that separates the two populations, astronomers believe, and I'm not an astronomer, but I read a lot. So they think that it basically after that radius you start breathing like a lot of gas, so this atmosphere is substantial. So then you have to include it in your model of layers and like see how it plays around it. It's like I couldn't say anything right now because it was not considered in my study.
I would also love to know, so you mentioned, so like you get these frozen cores, assuming that the temperature is below 10,000 Kelvin. Do we have like a good sense of what the temperature should be so that we should expect if we do
That
have
is
the
the
frozen?
question I've been asking to every single colleague that I see presenting something similar. It's like, how did you calculate the temperature? How do you know like how hot a planet is at the beginning? And you will read the papers with like crazy profiles of temperature, just assuming a number. It's like they really don't have any idea like what the exact temperature is at the beginning because it's very hard to calculate. But there are estimates from like from all these collisions that I showed in the video at the beginning. You can kind of estimate how much gravitational energy was accumulated and associate that to a temperature. But it's very uncertain. It's like we don't even know for the planets of our solar system, so let alone others. But this study that I presented already contradicts many others that like assume a temperature that was like too low already. It's like they would never get like an outer core, a liquid outer core, and they were working with that because they didn't know the melting temperature of fire at those conditions. And now I'm saying, hey, that's like mixed. It's nonsense.
There are not any questions on Zoom. I think then, if that's all the questions, let's give both of our speakers another big round of applause. So we'll do one more transition to plug our next seminar that will be coming up on.
Do you have the speaker?
I don't have the info just yet, but that'll hopefully be coming soon.
Alright. Yeah, so thanks again to Felipe and Isaac for the really interesting talks. I definitely learned a lot. And if you are interested in coming to our future seminars, which happen every third Tuesdays of the month, please scan this QR code, join our mailing list, and also check out our website and also our YouTube channel for the archive of past videos. And and if you have any questions, our speakers may have some time to stick around and you can ask them. And yeah, thank you so much for coming, and we'll see you next time.
For organizing.
Thank you for presenting.